Okay, so let me just tell you what this is about. So, in fact, Hacking the Universe is a code name for a book that I've just written called Programming the Universe. And the idea behind this idea of hacking the universe is as follows. So, look at that. So it's not a secret that we're in the midst of an information processing revolution. Right? I mean, in fact, indeed, as this conference technique shows, even though it's a miracle that I can appear to you there in India, and you can appear to me there. Can you wave to me so I can see that you're still here there? Oh, nobody. Okay, Neil's waving. Okay, good. It shows you that not all the.
Can anybody else here wave? Let's just test. Okay, no, Seth, they're here. I can confirm that now.
I see that. I see you all. In fact, I'm looking at on my screen. I have you rather than my presentation, so I'm looking right out at you right there. It's not a secret we're in the midst of an information processing revolution based on optical and electronic communications and electronic computation. But it's not clear yet that this revolution has a greater effect than the previous information processing revolution, which was the invention of type for books. And indeed, that information processing revolution, the invention of books with movable type, is certainly not necessarily greater than the invention of writing itself. And writing itself is perhaps a lesser revolution than the invention of language. And language, which stems from the invention of, if you like, or the evolution of the brain, which itself was an amazing information processing revolution. And if you go even further back, the brain couldn't have come into existence were it not for the origins of life itself, which at bottom, as we've learned in the 20th century, is a huge information processing revolution in which information is stored on DNA and processed via reproduction and natural selection. Okay, so you can see that the world is this history of information processing revolutions, in which the one that we're relying on here for our connections between Emil's office at MIT and that you're found in India is only the latest. Now, each of these information processing revolutions relies and goes beyond the developments of the previous one. Now, what is the origin of all these information processing revolutions? For instance, where does life come from? Life seemingly only began, at least on Earth, on the order of 4 billion years ago. But the universe is 13.8 or 13.7 billion years old. What was the previous information processing revolution? And my claim is that the original information processing revolution began with the Big Bang. And indeed, as soon as the universe began, it began, as it were, to compute. The universe processes information. Every elementary particle, every photon, every electron, every atom stores bits of information. Whenever two electrons or photons come together, bounce off of each other, they
one question.
Charles?
Charlie, great. I knew I could rely on Charlie.
I'm a little bit afraid that in the 19th century, people would say, or the 18th century, that the universe has been a giant steam engine ever since its beginning. Are you not now describing what people have always known in the most latest fashionable language?
Absolutely, I'm certainly open to accusations of that sort. Indeed, this metaphor of things as machines, which was a very powerful metaphor, and essentially drove first the Enlightenment with its creation of modern science in the West, and then the actual creation of machines in the Industrial Revolution. This was a very powerful metaphor. And so, of course, for instance, at the beginning of Hobbes' Leviathan, he talks about the human body as if it were a piece of clockwork. So he had a machine that he knew, a clock, and he said, oh, well, the heart is like the pendulum of the clock, and the muscles are like the wires that bring force from the weights, and the gears are like the brain, etc. So naturally, in talking about the universe as a computer, I'm guilty of the same kind of metaphorical talk that people like Hobbes and then everybody else for the next 300 years were guilty of. However, the point is very good. But, however, I would actually like to claim, and let me give the evidence for it now, that, in fact, people have known this, that the universe effectively computes, that every atom registers information. People have known this for almost 150 years, for long before the invention of digital computers. And indeed, the basic ideas of information and information processing, that is, the notion that every atom stores a well-defined number of bits, and the formula, the mathematical formula for information, to describe the number of bits atoms register. These were developed in the latter part of the 19th century by people like James Clerk Maxwell, Ludwig Boltzmann, and Josiah Willard Gibbs. Indeed, the people who founded statistical mechanics were, in fact, the people who worked out the formulas of information theory, realized that all atoms register bits, and developed equations, such as Boltzmann's equation, that describe how that information is processed when two atoms collide. So, even though I'm guilty of this of using a metaphor for computers as a popular thing and describing the universe as that, I also claim that, in fact, there's very solid science
Okay, so Seth, carry on.
Go ahead, go, sorry.
Absolutely, no, please keep heckling me. Other people heckle me too, I like that. I love being heckled from the other side of the world. So, and if you look at this formula, we see that the real formula there, what we're looking at, is a formula that was later developed by Nyquist. Information I is the logarithm to base 2 of W, the number of states. Because, if I have a system that has 2 states, it can register 1 bit. If it has 4 states, it can register 2 bits. If it has 8 states, it can register 3 bits, etc. So these mathematical formula that were developed by Maxwell, Boltzmann, and Gibbs actually are formula for information. And the quantity that they call entropy, the quantity that they've been desperately seeking the mathematical formula for, is in fact a measure of information. Entropy is the information that we lack about the microscopic motions of molecules as they move all over the place and collide into each other. Okay? And indeed, the famous Shen formula, which is on the last slide of this transparency, I hope you could read it. I did use a rather low bit rate for this transparency in order to email it around. It essentially says that information is minus the sum over the different states of p sub I log p sub I, a quantity that Shen called H in his famous paper. Why did he call it H? Because when he went to John von Neumann and said, hey, I found this great quantity that measures information, what should I call it? Von Neumann said you should call it H, because that's what Boltzmann called it. Right? Actually, Boltzmann called this minus H, which led to a lot of confusion later on. But the point is that the basic formulas of information theory developed in the end of the 19th century by people who had no notion of electronic computers. And the notion that information was processed when 2 atoms collide is in fact the basis for Boltzmann's equation. Indeed, Boltzmann's equation is a way of analyzing what happens to information when 2 atoms collide. And Boltzmann's equation essentially says when 2 atoms collide, they attain mutual information about each other, and so their individual entropy increases. So if they're in a case where you know more about them to begin with, and then they collide, then you know less about them afterwards. And that's the basis for entropy increasing in Boltzmann's equation. Boltzmann's equation is a statement about information processing. Okay? So this whole notion that the universe is effectively computing is an old one. That's what I want to say. And I'm just saying it again in language that we can understand. All right, are there any more questions at this point? Okay, good. Yes, I noticed that when I put my finger out like this, it gets closer and closer to the camera there. It looks rather ominous from this end, so I don't want to intimidate people from doing this. Let's go on. So what does this mean in the case of something like an atom? So Boltzmann, in the case of an atom, he essentially said they didn't know about quantum mechanics back then. It wasn't until Planck figured this out right at the turn of the 20th century. So they essentially said, oh, well, let's suppose that we have some atom that's moving along. Here's its position, and its position is only defined to an accuracy delta x. Well, then, the number of effective states of this system is essentially the logarithm of, well, the number of effective states is the range x divided by delta x. And the information in this position is just the logarithm of big X divided by delta x. That's the number of bits that's registered by this atom. Okay? Now later on, Planck came and showed that indeed there's a natural scale in phase space given by Planck's constant. So if I have a range x for position and p for momentum, then there's a little range, Planck's constant, which is delta x times delta p. And what you see is that the formula for entropy is just the logarithm of the range in x times the range in p divided by Planck's constant, delta x, delta p. Planck, of course, originally used quantum mechanics to try to resolve a question about entropy, which we now would realize is a question about quantum information. He wanted to show that the amount of entropy emitted by a black body, such as an oven, that's emitting hot radiation, that this entropy is finite, because if you calculate it classically, it's infinite, both the entropy and the energy. And this paper on the gathering of entropy by intelligent beings and on Maxwell's D-net, I don't know that if he was actually, he had a quantum mechanical model in mind. Charlie, what do you think?
I don't think there's a mention of quantum
Because the
mechanics
reason
in
I
that
ask is,
paper.
your spin is nice, but it also leads to a testable prediction, possibly about causality in Szilard's influences, which I don't know anything about.
Oh, I thought you were going to talk about David Deutsch's notion of time travel via entanglement. So perhaps you could, these ideas were implanted in their minds via some errant time machine. That's also possible.
The question is, did Szilard write his paper with information in quantum mechanics kind of in the air, or did he detour around it and follow Maxwell and Boltzmann?
No, in fact, the notion of applying information to quantum mechanics was missed by all sorts of people. I mean, you would think that von Neumann, of all people, having written, his groundbreaking textbook on quantum mechanics, would have, and also be one of the founders of information theory and statistical mechanics, would have thought of quantum computers. But as a number of people, including Charlie, have pointed out, he evidently didn't think about this. I read his collected works, and in none of his published works, or in any of the works collected in his collected works, is there any information or mention of quantum information? It really seems that it wasn't until until Charlie and Rolf Landau and other people came along, and then until Paul Benioff wrote his paper on quantum computers in 1980, that people started to think about this. But the ideas were there, right? Indeed, we should have been trendier earlier and applied these notions earlier. In fact, I think that this whole notion of applying the idea of universe as a computer is a rather late comer to the actual science of looking at the computational power of the universe. Okay, don't want to go over here, so let's keep going. So here's an example. Here's, of course, what we do now, and indeed, I'm basically a quantum mechanical engineer. I work with people like Jeff Kimball or Dave Corey or Yasunori Nakamura, Hans Moy. Lots of wonderful scientists could manipulate information at the quantum mechanical level. I work
Ike, can you hear me?
Like, yes, Neil.
Do you have a presentation?
I do. It's on a memory stick, and we'll just put it on this laptop here.
No, that laptop isn't running the VNC. The VNC is on the server. That's just running a web browser to it. If you can't run a VNC server, you need to email it to me, and I have to put it onto this server.
Okay, I'll try to run a VNC server here for you. It'll probably be easier.
Quickest would be is if you can quickly install type VNC and tell me an IP address, and then I can add it to the conference. Okay?
Understood. Give me 5 minutes. Yeah. See, there we go. This is what I'm talking. You know, the universe is out of control. And why is it out of control? Because of all this new forms of information processing. Okay, so let's go on there. While Ike tries to do this magic, which I'm glad it's not me, is all I can say. I'll look at him every now and then. I'll tell you if he's sweating or not. Okay, so now let's look at different ways of hacking the universe. What are different ways of building quantum computers? Well, I described to you how you can make quantum computers out of arrays of atoms. You can also, a very famous example of quantum computers first realized, proposed by Ignacio Serac and Peter Zoller, and first realized by Dave Wineland at NIST, is to put a bunch of ions in an ion trap. They're trapped there, so they not only do they have internal states like the atom, like internal spin states. Look, the universe is speaking. I like that. What does it have to say? If it interrupts me with something good. Okay, so the ions in the ion traps have internal degrees of freedom, internal bits, and then they have this nice rocking mode, which is a phonon mode.
in terms of information a career-ending black hole?
Yeah, good question. Yeah, well, a few years ago, inspired by one of my favorite computers, which ended its life as a black hole, I decided that it would be interesting to look at whether black holes could compute and how they compute. Let me actually just go on to the next slide, because this is related to this. So, in fact, let me use Neil's question to, I'll get to this in the transcript of the slide after this, but let me just talk about this for a second. So, my reason for building quantum computers, selfish as it may be, is not necessarily to factor large numbers. The world is divided into people who really like to break other people's codes and people who don't care so much about it, and I'm in the group that doesn't care so much about it, okay? Nor am I so concerned about security of my computer, because who steals my hard disk steals trash, right? My reason for looking at quantum computing is, and always has been, to understand how the universe works and processes information at its most fundamental scales. So, and it's a fact, actually, that I showed a few years ago, that if you look how quantum computers and quantum communication systems flip bits, they actually flip bits at the absolute limit allowed by the laws of quantum mechanics. So we have a limit, delta t is equal to 2 pi h bar over 2 delta e. This is the familiar Heisenberg limit for bit flipping. It says if you want to flip a bit in time delta t, you have to have a spread in energy of your system at least pi h bar delta e, such that pi h bar over 2 delta e is equal to delta t. And then there's another less well-known theorem called the Margolis-Levitin theorem, which is equally or perhaps more useful, which tells you that the amount of time it takes to flip a bit is limited by pi h bar over 2e, where e is the energy of this qubit over its ground state. And if you want to verify these in a simple case, just take the case of the nuclear spin that I described before. Spin up, spin down, a nuclear spin and magnetic field pointing sideways will precess around like this, will precess at a frequency omega, its Larmor frequency. The amount of time it takes the spin to rotate from here to there is exactly limited by both this Margolis-Levitin theorem and the Heisenberg limit. It saturates these bounds. So, quantum mechanics in general limits the accuracy to which quantities such as charge, energy, distance, time, etc. can be measured. And quantum devices can be built that approach these limits, such as quantum computers. So I think this actually gives us hope for Feynman's famous dictum that there is plenty of room at the bottom. The bottom is incredibly huge. The small scale, how small it is, doesn't depend, how big the small scale is, doesn't depend on its absolute size. It depends on, as in that earlier transparency, the ratio between the size and the smallest distance you can effectively control. The number of bits you can cram in is the logarithm of the ratio between that and that. And if we can control this to the level of atoms, then the nanoscale is huge, as Feynman pointed out. Okay, so now let's get to crazier stuff here. Let's actually look. So as Neil alluded, I've been spending a fair amount of time over the last 6 or 7 years developing a theory of quantum gravity based on quantum computation. Now this, of course, is exactly the creating black hole kind of thing that he mentioned. Though, in fact, attending quantum gravity conferences, I can't, for the life of me, see that other theories, such as string theory or loop quantum gravity, are at the point where we should be intimidated by them and not come up with alternative theories of quantum gravity. But let me give you not the theory itself, but the justification for this theory. I just want to make sure, tell me, Neil, when you want me to stop here, or give me a 10-minute warning or something.
10-minute warning.
Okay, good. So here's the justification. Good, that's fine. So here's the justification. Think of the global positioning system. So I've drawn a picture here of a bunch of clocks moving through space. Space goes horizontally. Time goes up in the lovely way that general relativists like it. So for engineers, time goes from left to right. From physicists, it goes volume of space-time, that at a certain point something happens. That what happens is this volume of space-time becomes a black hole. We've crammed too much energy in it, and light can no longer escape. Now, I have nothing against black holes. As I said, my favorite computer ended its life as a black hole. But if part of your GPS network becomes a black hole, that's bad. You can no longer measure the volume of space-time, measure the geometry of space-time within that volume, because that part of the GPS network can't even communicate out any longer. So the information about that volume of space-time is now lost to you. Okay? So we have to keep the energy density lower than the Schwarzschild limit. The Schwarzschild radius is 2gm over c squared, which is equal to 2ge over c to the fourth, using Einstein's famous formula E equals mc squared. This implies if you put this bound on the number of ticks and clicks from the Morrow-Gillis-Levitin theorem together with the Schwarzschild bound, then the total number of ticks and clicks, the total resolution to which you can map out a volume of space-time, is limited by the spatial extent times the temporal extent divided by a resolution. But the resolution now is not just the quantum scale, but the Planck scale, the Planck length times the Planck time. In other words, at this factor of 2 pi. So the total number of ticks and clicks you can cram into a volume extent x of length t is limited by this area divided by 2 pi times the Planck scale. It's an interesting result. It's closely related to and consistent with the holographic bound that puts limits on the number of bits you can cram into some volume. But this limit actually implies, notice that I derived this without having to apply to quantum gravity or anything like that. This is simply a limit on the quantum mechanics of measuring space-time combined with a reasonable demand that my measuring apparatus not collapse, undergo gravitational collapse. Okay? So this quantum geometric limit is not a limit of quantum gravity, or is not derived in quantum gravity, though one should hope it would apply there. It was derived simply by applying the normal physics of measurement to the normal fit to a reasonable demand on how we measure self-gravitating systems. Now, if this does indeed apply to gravitational systems, and indeed I would certainly hope it does since it's so simple to derive, then we actually have to make statements about the universe as a whole. In particular, the total number of ticks and clicks, the number of elementary events that can be crammed into the universe as a whole, is in fact less than the age of the universe, 13.8 billion years, squared, divided by the Planck scale squared, which is around 10 to the 122. Only about 10 to the 122 elementary events, ticks and clicks if you like, or collisions of atoms, or flips of bits, can have occurred since the universe began. This means that the resolution to which the universe is actually mapped out by the matter within it is far less accurate than that normally thought. Normally people think, oh, it's the Planck scale. In fact, it is not. The resolution on average to which we map out the
you are saying essentially that the universe is a non-trivial dynamical process when you say that it's a computer. And I wonder, I think that's we would probably all agree with that, and maybe even Maxwell and Babbage would have agreed with it. But I wonder if you want to become more quantitative than that, are there incomparable kinds of computation? I think probably not. Computational universality means that any computer can simulate any other. But I wonder if there are kinds of natural processes or kinds of dynamics that are perhaps mutually hard to hack, or one can hack the other but not so easily the reverse. So that to build up some kind of partial order of computational complexity of the dynamical processes in physics.
Yeah, that's a really good question. Yeah, so indeed, what is known is that if you have local interactions between quantum systems, and you can control those local interactions, then first of all, any such system can be a universal quantum computer, and also any such system with controllable interactions can effectively, efficiently simulate any other system with local interactions. However, if you have systems that have global interactions, well, and also at bottom we believe there's strong evidence that the laws of physics involve local interactions, so maybe that's all that is. But certainly, at the scale of building devices in the laboratory, in the time scales and length scales that we have systems that have large, long-range, non-local interactions, and it may be very hard or exponentially inefficient to take something that has very long-range interactions and to turn it into something that looks local. Indeed, it would be quite interesting, I think, to try to give an example of such a system where that can't be done. Let me actually just say, since you brought it up, there is one thing, one prediction, if you like, or this is prediction in the sense that people in the quantum gravity or string theory world use the word prediction, which really means a retroviction, okay? So one feature of the universe that its computational nature explains. So let's suppose that the universe is, in fact, a universal computer, not merely a non-trivial information processing system, but capable of universal computation. Indeed, since universal computation is ubiquitous, it would be very hard. It's hard to imagine how it wouldn't be. Well, then you can prove mathematically that the universe is what you, Charlie, have called an ambitious system. Right? It's a system like a computer, which is being programmed at random, in this case, being programmed by little quantum fluctuations everywhere. These quantum fluctuations act like the zeros and ones, which they program the universe to do interesting things. And as you yourself have pointed out, and is implicit in the work of Chaitin, Kolmogorov, and Solomonov, if you take a universal computer, like the universe in this case, and you program it at random, in this case programming it with quantum fluctuations, then it is highly probable, nay certain, that somewhere, someplace, sometime, something interesting is going to happen.